Hello, welcome to our 7th lecture on lines and slopes. We are now officially out of the review section in the book. It'll still be about a week before we get to the uniquely calculus content. I'm looking forward to that. But we still have some fundamentals to build on. So, lines and slopes. Let's start with a basic graph. I won't get too particular about it. I've got my y-axis and x-axis. Okay. And a line. So first off, I'm going to point out these two unique points where the x and y axes are crossed. So these are called intercepts. The x-intercept, where you cross the x-axis, and the y-intercept, where you cross the y-axis. Now let's look at a couple generic points off to the side. I'm just going to call this one x1, y1. And another one up here, let's call x2, y2. Now, what happens when you consider these two in relationship to one another? In particular, their distance in terms of both x and y. So this y distance here between the 2 points, I like to affectionately call the rise. And horizontal distance, the x direction, we call run. So we're about to talk about slope in a second, but I do want to point out, before I've even really mentioned what it is, this line has positive slope. And you can tell based on the graph, based on the picture, it's when the line rises from left to right. So when you're reading from left to right, which is how most of us are used to reading, the line's going up. So that means we have positive slope, or in other words, the slope is a positive number. Slope is essentially a measure of how quickly your line is rising. So a very high slope means it's very steep, your line is. A very low slope means that, like, say slope 0, for instance, means that you're flat. And we'll see what that looks like in a minute. So remember when I said rise over run? Rise over run. All you have to do is pick two distinct points on your line, any two different points. And if you do this little calculation, you'll find the slope. And it's the same for every pair of distinct points. So that gives you a lot of flexibility. So think of this as change in y over change in x. This is a delta Greek letter that represents change. And the way this bears out in the calculation, so I labeled my x and y values for my points. You take the difference in the y values divided by difference in the x values. Now you have to be careful. because once I've chosen this to be my y2, then I have to write the x value for the same point first down here. So that's important to get that matching up properly. Let's do an example. Find the slope of the line with points 1, 1 and 3, 5. We're not even providing a graph, just 2 points on the line. That's all you need. So m is rise over run, difference in y divided by difference in x. So I'm going to pick this y value first, 5, minus the y value of the other point. And since I chose 5 first for the y's, that means for the x's I have to choose 3 first. That becomes 4 over 2, reduces to 2. Now what matters is that you're just consistent in your choice. Like I chose to use these values first, and then these second. But I could have gone the other way around. So let's just look at that real quick. If I chose the 1 y value first, this is fine as long as I write the 1 first for x. Well, that'll make both of these negative compared to the previous numerator and denominator. But because they're both negative, when you divide, those negatives cancel. So you get the same thing. And just a rough idea of what does this look like. I wouldn't say this is required for this problem. We got our answer, but just want to show. All right. We had the point 1, 1, and 3, x equals 3, y equals 5. So to plot that point, connect those little dotted lines. Okay, now connect. And that gives us our line. So that's what a slope of 2 looks like. Another way to think about it, you start at some point, like here, for instance, and to get to my quote-unquote next point on the line, I can go up 2 units and over 1 to the right. Then I land on a new point on the line. Let's talk about equations of lines. First, let's talk horizontal lines. So brief picture. I'll use a different color to make it clear. And let's say we have this particular point, x equals 0, y equals k. K is some number. Let's look at the slope. Well, slope is rise over run. And for this demonstration, I'm not even going to pick 2 points. because you can see that, say I pick this point and some other point over here, that no matter what pairing I choose, the rise between those two will be 0 because they have the same y value. Now, the run, of course, will be something other than 0, but that doesn't really matter. 0 divided by some number, that's not 0, will get you a slope of 0 no matter what. So horizontal lines are always slope 0. The equations have the form y equals some number k. This k up here. Now, that might seem a little counterintuitive at first because it's a horizontal line. We think of that as like an x kind of thing, but the equation has no x's at all. But when you really think about it, this is correct. The fact that x is not there means that it's free. It can be anything. We have no restrictions on it. But this equation gives us a restriction on y. Y equals k. In other words, this is the set of all points whose y value is k. So horizontal lines, every point has the same y value. Now their counterpart, vertical lines, something like this. And let's say this point is x equals k, y equals 0. And yes, let's label this as vertical lines. Let's take a look at the slope. Slope is rise over run between any two distinct points on the line. We'll notice that in this case, the run will be 0 if I pick any 2 points, like say this up here in the k0, because the x values are going to be the same. So that's true for every pair. And rise will be something non-zero. Remember that it's bad to divide by 0. This is an undefined slope. In a sense, you could think of it as the slope is infinite, but it's really best practice to say undefined. So this is unique to vertical lines. They have the undefined slope. And the equation has the form x equals k. Every point on that blue line has an x value of k. Now, general lines. I've been drawing a lot of positive slopes so far. So here's what a negative slope looks like. As you read from left to right, it's going down. So that's a very special place. I'm going to label that y value b, where we cross. And this is just some generic point. Let's call xy. So when we talk about an equation, what we're saying, points of the form xy on the line, they correspond to solutions of the equation. Okay, down here. So what a general line equation looks like. Y equals mx plus b. All lines can be expressed in this way except for vertical, because they have the undefined slope. M is slope, and b, that's that special place where we cross the y-axis. Call that the y-intercept. Now we call this form slope-intercept form. And you can see why, because it has the slope and the y-intercept. M and B are very clearly displayed. So that can help you remember this form, the name of it. Let's put this to use. I want to start abbreviating equation. Find the equation of the line, and now I'm going to graph this. Let's go 4 units in the x direction and 3 down. And draw those 2 points. And then connect. So if I want to find the equation of the line, especially in slope-intercept form, I need the y-intercept and the slope. Well, we can see the y-intercept clearly displayed there. And the slope, well, we can determine that because we have 2 points. This point is 4, 0 to be extra clear. At this point, the x value is 0 and y value is -3. So I'm going to use this 4, 0 first. So that y value is 0, and that's minus -3 over 4 minus 0 becomes a positive 3/4. Then y equals mx plus b, that's -3. So there's an equation of the line. If I plug in any x value, then this equation will give me the y value of the point on the line that has that x. So solutions to the equation correspond to points on the line. This was a nice example, but what if it's not so nice? What if I don't have the y-intercept? It turns out that there are other forms that the equation can be written in, and that'll be helpful in this case. Sometimes you don't have the y-intercept. In that case, point-slope form comes in handy. Let's suppose our line has slope m and point, I'll call it x1, y1. Then point-slope form looks like this. Y minus the y value of that particular point equals m times x minus the x value of that point. This will work for any point on the line. The equation might look a little different, but it'll all describe the same line. Let's try this out. Find the equation of the line and all that we're going to know ahead of time is 2 points on the line, and neither of them will be the y-intercept. I'm going to be a bit particular here. I want this in slope-intercept form. Now this is the y equals mx plus b form, so that's not what we just talked about, but we'll get there. The trick is to first write in point-slope form, because that'll be easiest based on the information we have, and then we'll convert to slope-intercept. So this is a bit of a two birds, one stone example, where I'm also showing you how to convert. So first write in point-slope form. Then you can convert from there to slope-intercept. For both forms, you need to know the slope, and it's in the name. We can find that pretty quickly because we have 2 points. The 1, 1 and negative 3, 7. So I'll write the y value of 7 first. That means I have to write the x value of negative 3 first. Also minus 1. That gets me 6 over negative 4, reduces to negative 3 halves. I just like writing the negative above, but it's the same thing. So now the equation of the line in point-slope form. It doesn't matter which point I pick to be my particular point. It can be either one. I would pick the one with simpler numbers, like 1, 1. So y minus 1 times slope times x minus the x value of my point. Here's the equation of the line in point-slope form. But remember, the problem says to write it in slope-intercept, which means we have to convert. The trick to convert to slope intercept, and that's the y equals mx plus b form. The trick is to use algebra to solve for y. And you may need to do some simplifying too. And on that note, first I want to distribute this 3/2, or negative 3/2. And that'll be a plus 3/2. And now I can just add 1 to both sides so that I get y by itself. Plus 3/2 plus 1. And we have some like terms here. We can combine those. Think of 1 as 2 over 2. I'm not going to show all that work. That gets you to 5/2. So this is the same line, but now in slope-intercept form. So it just took a little algebra to get there. Now there's yet another form, a third form, which does show up in the homework, so we'll talk about it. This is standard form. And ironically, out in the wild, or at least in these sorts of classes, this is probably the least commonly used form, but it's still good to know. So some of the features, you have x and y terms on the same side. That's unique compared to the other two forms we've looked at. A and B are real numbers. Oh, sorry, excuse me. It's not 0, but C. It can be any real number. So I have these 3 real numbers, A, B, and C. Now we can make it so that A, B, and C are integers. So that's what we want. And especially with no common factors. That means that this equation will be as reduced as possible. So for example, if A, B, and C were all 2, then they all have that common factor of 2. And if you just divided both sides by 2, you would then have a simpler equation. So that's what we mean by no common factors. Just means you can't divide out something to simplify. And one more thing. I would say this is not always the case, but this is how your homework likes to do it. So we're just going to say that A is non-negative, or it's greater than or equal to 0. So no negative coefficient with the x. We'll get to an example with that, but I also want to mix that, for the sake of time, with another concept of parallel lines and perpendicular lines. If I have 2 lines, we say that they're parallel if they have the same slope. It means they're rising at the same rate, and hence they'll never cross one another. So if you encounter a problem that asks you to think about parallel lines, that just means you have a different line but with the same slope. Now you have this similar concept, perpendicular. Now this has to do with slope as well, but in this case they're not the same slope, but a special relationship. So two lines are perpendicular if their slopes are opposite reciprocal. When I say opposite, I'm talking about negative, and reciprocal means 1 over the thing. So we're just going to do one example related to this, and I'll focus on perpendicular since that's a little more challenging than parallel. And we'll connect this to standard form. We want to find the equation of the line perpendicular to this line, 2x minus y equals -9. And you have to say a little more. That word didn't go through there. Oh, oops. Right, I have the line, the line perpendicular to 2x minus y equals -9 through the point 2 1/2. And in particular, just so we see this, I want it in standard form. So first, let's think about the slope. Well, the slope of the original line we're looking at, it's not immediately obvious because this is in standard form, but all we have to do is to convert to slope-intercept form. So first we find the slope of the line we know about. Just do a little algebra to solve for y. Means you would add it to both sides to move it over. And you would also add 9 to both sides. And you see, oh, okay, the slope is 2. When you're in slope-intercept form, it's the x coefficient. Well, once we know that, the slope of the perpendicular line by definition, that will be the opposite reciprocal of 2. That's what it means to be perpendicular. So the opposite means negative. Now, if our starting slope were negative, that would mean you would take a double negative, hence a positive. But here we end up with negative. And reciprocal, that means 1/2, that 2 goes to the other side of the fraction bar. So the slope of the line we're looking for is -1/2. Okay, so I know the slope, and I know a point, because that's part of the problem. It tells us we're passing through this point. So if I know a point and a slope, that means I could use point-slope form. So this is or just 1/2, is the y value of the point. And this negative 1/2 comes from the slope, x minus 2. 2 is the x value of the point. So this is an equation for the line we're looking for. This is valid. It's just not what the question's asking. We want it in standard form, not point slope form. So to do that, we want to simplify first. So I'll just go ahead and get us to slope intercept. Distribute this negative 1/2. A negative 1/2 times negative 2 is a plus 1. Then I'll get y by itself by adding 1/2 to both sides. And I don't want to write a whole other line. 1 plus 1/2 combines to 3/2. So y equals negative 1/2 x plus 3/2. That's the line in slope intercept. Now to get in standard, remember that for one thing, every number that appears must be an integer. These are not integers, they're rational numbers and fractions. So if we want integers, the trick is to clear the denominators by multiplying. We multiply both sides by 2 in this case. That'll get rid of those halves. You have to do this to both sides, so that's happening to the y as well. I get a 2y. That'll make this just a negative x plus 3. So we're closer to standard form. Now in standard form, you have the x and the y terms on the same side. Right, if we scroll up for a moment, right, it looks like this. You need the x and the y terms on the same side, and then the constant by itself over here. Remember that we said we wanted a to not be negative, so whatever number is in front of the x shouldn't be negative. Well, right now it is. So that means I want to move the x over here rather than moving the y over instead. So we need our a greater than or equal to 0, which means I don't want a negative x. So I add x to both sides to move it over. Now we have positive x. Great, so now the x and the y terms are on the same side, and the x coefficient is positive. Could be 0, but in this case it's not. And every coefficient, or let me say this, there is no common factor among all of the coefficients. Right, 2 and 3, no common factor there. And of course 1, you're not going to have common factors with anything else. Which means this is as reduced as it can possibly get. There's nothing to divide by. So this is the line in standard form. It's perpendicular to that line we mentioned at the start, this one. and it passes through this point. You can check your work by plugging those numbers in, 2 for x, and you should get y to be 1/2. Well, I guess in this case you would plug in 2 for x and 1/2 for y, and notice that you indeed get 3. Let's end our time together with a word problem. Normally I don't write everything out ahead of time, but in this case it's a lot of writing, so it makes for a better video if I just have it all ready for you and you can pause if you need to if you're taking notes. The sales of a small company were $61,000 in its 4th year of operation and $89,000 in its 6th year. Now we're going to make a model where Y represents sales in the Xth year of operation. Assume that this data can be approximated by a straight line. So that's a steady rate of growth, in other words, over time. Let's find that equation. I'm going to ultimately do this in slope-intercept form. We like that nice y equals mx plus b. But right now, all that we know is effectively 2 points. And neither of them is the y-intercept. I know that when x is 4, y is 61,000. Right, this is the sales y in the xth year. And also when x is 6, we have sales, our y value of 89,000. So we know 2 points. About another colon there. X equals 4. The y is 61,000. I'm just going to avoid the comma because we already have a comma here that's a little confusing. 6. Oh, that was 89,000. So if I just know 2 points and I don't know the y-intercept, then I want you to think for a moment, what is the form that's best suited for this? Right? Is it slope-intercept or point-slope or standard? I'd say the answer is pretty much never standard. So out of those first two, we'll think in terms of the names. We don't have the y-intercept, but we do have points. We have 2 of them. So I'm going to do point-slope form first. We'll still need the slope. Or excuse me. Change in y over change in x. Okay. So we'll get 28,000 over 2, 14,000. Notice that this is a positive slope, which means that as x increases, so does y. So we're making more and more money every year. That's because we have a positive slope. And that's a good place to be. So I know the slope now, and we have a point. We have 2 points, but we just need 1 now that we know the slope. I'm going to use the one with smaller numbers. Oh, that's y minus the y value equals slope. times x minus the x value. So this does technically work, but I would like my final answer to be in slope-intercept form. So I just have to simplify this and solve for y. Let's start by distributing that 14,000. So multiplying that on to -4 gets me 56,000. And then to get y by itself, I add 61,000 to both sides. Plus 61,000. Now we can simplify these two combine to get me a positive 5,000. So 5,000 is the y-intercept. That means when x is 0, y is 5,000. And by the way, you can actually see that in the equation. If I plug in 0 for x, then this becomes nothing. And then you have y equals 5,000. It's a neat little thing. So there's the model, and now let's put it to use to wrap this up. How many years before sales surpass $110,000? So we have a desired number of sales. Okay. And we're looking for years. How many years? How many years? So that's an X we're looking for. So I know a particular Y, and I want to then find a corresponding X. So we use our equation, plugging this sales number in for Y. I don't know X. That's essentially what I'm trying to find. And then it's an algebra problem. So if I want to solve for X, I subtract 5,000 from both sides. That's a good starting point. So I'm just going to write the X part first. So when I subtract 5,000 from both sides, I'm left with 14,000x. And then on the other side, we have this 110,000 minus 5,000. And that will be equal to 105,000. And then to get x by itself, I want to divide off this 14,000. X is 105,000 divided by 14,000. Now these thousands will cancel. Think of this as 105 times 1,000. This is 14 times 1,000, so the 1,000s cancel. Makes things a little easier. Now, when you plug this into your calculator, you get 7.5. So that's not a very precise year number. Well, the problem is talking about sales surpassing that 110,000. So that means that we can round up because our sales will be greater. So picking 7 years, that does not work. because we will be under this amount of sales at that point. But the next best thing is rounding up to 8. And at this point, we will have surpassed 110,000 in sales in a given year. All right, well, next time we will continue building our fundamentals, although it's still outside the official review section in the book. But we will talk about exponential functions